download it from GitHub and copy. So for this exercise, my goal, my learning objectives for you guys is to first really learn where can we find the recommendation, even if you're applying a flat rate of any nutrient in any crop in the US at least. Where can we even find that recommendation? Like, what is the source? Where is that magic formula or number coming from? So we're gonna go through that quickly. Really understand what do we need to even come up with a variable rate nitrogen prescription in cotton? What pieces of information we have to make that, that prescription? And then we're going to estimate zone-specific yield potential. So yield potential for each one of those zones. Using that yield potential, we're going to do a variable rate nitrogen recommendation based on that. And then calculate the total amount of fertilizer that's going to be needed for that field, so we know how much we need to have delivered at the field to even do that, that application. And then finally export this variable rate map in a format that can be used by a variable rate controller. So we've been using GeoJSON all the way up until here. And if you remember, the reason for that is because GeoJSON is just one file, so it creates less clutter in our data, in our directories. However, Dr. Virk was mentioning that he didn't even mention GeoJSON at all. He said shapefile is the type of file that will be the most commonly used across different controllers. So that's what we're going to be exporting here. So we make sure that we have a file in the right format. Okay, so here's a question for you all. Maybe you've come across this before in different class, but how do we know how much nitrogen we should apply to a cotton field? Where do we even find that information? Any guesses?
There's literature about, depends on the yield, the lint yield you need, and it goes according to that. And I think Dr. Virk told us about the calculator that UGA has developed too. So yeah.
Right, that's great. Yeah. So normally, you know, these formulas and numbers come from research, right? It's not that somebody comes here and says this is how much we need depending on this. Is actually a lot of research goes on behind the scenes to even develop these algorithms to give us that relationship, in this case, between yield potential and nitrogen rate. So definitely on research papers, we will find that. However, because that is such an important piece of information for producers, normally this piece of research really gets into extension publications, which would be, you know, really looking at consultants, farmers to really use it, but also makes it easier for us when we're trying to find that information. So you don't have to go through Google Scholar and do a literature review. You just basically type cotton nitrogen recommendation, Georgia, and you hopefully will be able to find something like that. So I want to show you here. So here at UGA, there is the cotton team that basically is a group of researchers that work around cotton, and they put together the cotton production guide. Every year, as far as I understand, there is a new publication, which I have a link right here in the script for you. And I just launched that link here just to show you. This is what the Georgia cotton production guide looks like. It's a PDF online, it's free. You have access to it. And it really has, it's like a whole book pretty much on managing cotton. And one of the things is fertilizer management, right? But it has a whole bunch of other things like irrigation, weed management, other nutrients. I mean, a whole bunch of things as far as recommendations on an extension facing publication. So I opened that here. It has a whole bunch of things. I'm just going to scroll down to where, so there's a fertilization section, and within that, it has a nitrogen management section. Okay, so here is, I think maybe we've seen this table here before, but really what this table here is doing is basically, as Johnny's mentioned, connecting yield goal in pounds of lint per acre to a nitrogen rate, right? And then below here, let me just increase the font so you can see better. it has some extra recommendations here. So once you define your yield goal and you find your recommendation, it says here to increase your nitrogen rate by 25% of whatever you find on the table if you are within one of these conditions of deep sandy soil, cotton following cotton, or a history of inadequate stock growth. And also the recommendations if you need to decrease by 25%. So I'm not going to go through this extensively. I just wanted to show you for Georgia where you'd find this information. And you know, different states in the US have their own recommendation for all the major crops of that state. So if you were to look for this, you know, even a different crop in Georgia, maybe corn, or maybe if you go to a different state, you would always look for these extension bulletins that have that information there for us, okay? This is the source of that information. And the tool that Dr. Rick showed us, that UGA Vertex, perhaps is the name, maybe I'm missing the name, but that online tool is basically a representation of all of these formulas, but on a web tool, pretty much. So this is the source of the formulas that are feeding into that web tool that we saw. So this is the source. Okay, so from that table, we can really tell that.
Can I rain on your parade for just a minute?
Yes, yes, please go ahead.
So what Dr. Bastos told you is exactly correct. However, growers really need to understand the yield potential of their field before they go to that table to select what their yield goal is. And in too many cases, that doesn't happen. So everyone wants 3-bale cotton, but you can't grow 3-bale cotton on every field, right? So you have to have the good farmers understand their yield potential and they tailor their expectations accordingly. Although there are people who say my yield expectation is 3 bales everywhere, regardless of what my soil can really produce. And then we have the situation where we're over applying fertilizers and causing other problems. But experienced farmers know this intuitively, or they know that by studying their soils, but they don't just apply the high yield just because that's what they want to achieve. Right, so we got to keep that in mind as well, right?
Yeah, that's a great point, George, especially because we're going to do that calculation right here. And I want to show how we would estimate yield potential, not on a field basis, but on a zone basis, because we have already defined, we have 2 zones, one low, one high potential. So we need to first, well, I'm getting ahead of myself and probably answering some questions that I will ask them. So I'll just stop speaking. But that's definitely very important.
It's so exciting. We can't wait, right?
I know. Okay, so here's the thing. Based on that publication, right? Our nitrogen recommendation is going to depend on the yield potential. If we should adjust that in plus or minus 25%, given some condition of that field. And it should also be, I mean, I didn't go through this part, but normally, and it is recommended on that publication, that nitrogen in cotton is split applied, and at least 1 split application, but possibly more. So I want to ask you this, and I want you to help me to answer here. For this field here, I want to assume that it is, well, let me not assume anything at this point and just ask you, what pieces of information do we need based on what I'm just saying above here? What do we need to know for this field to create a variable or to create a recommendation of nitrogen that at this point doesn't even have to be variable rate, just a recommendation for this field? What do we need to know based on this? There are 3 things that I at least came up with. Perhaps I'm going to ask one for, or a different person for something. Victoria, what do you think? What would be the first thing for this field that we need to know to create nitrogen recommendation?
Soil texture.
So soil texture is important, but is not something that is explicit in the recommendation itself. So what? Yield goal, yes, yield goal is the main one, right? Is the main driver here. So I'm just gonna write here yield goal, just so we know. And something else I want to now call your attention to the increase or decrease by 25%. And what, like, I mean, well, there's a lot of things going on here. So I just want to tell you, for this exercise, I want to assume that we're doing cotton following cotton, just like we had from 2019 to 2020. So in that case, we need to know the rotation, right? Like what came the year before. So if I am assuming, so the point number 2 here is the rotation, one of the things. And in our case, we're going to assume that it is cotton following cotton. And because of that, we'll have to adjust our rates upwards in 25%. And the third thing that, again, I didn't really read through it here with you, but look at this. The total end rate should always be applied in split applications. So then the third thing that it is important for us to define is how many applications we're going to have. So normally it would be one pre-plant or at planting and at least one more side dress, right? So really knowing, because we define the total rate first, and then we split that total rate in chunks that we're applying in different moments. So let's just say here, like, you know, how many applications we're doing would be the third piece of information we need to know. Okay, so more pieces may be important. If you look at those, like plus or minus 25%, there are different conditions there, like soil type, as you mentioned, other things that we should also be thinking. But for our case here, these are the 3 pieces that we need to know at this moment. Okay, so
can I ask something?
yes.
Yeah, another reason. Can you go back to the document again, please?
Mhm.
Is it okay to say that the we also have a history of inadequate stock growth because we had areas with consistent low yields?
That so that's a good question, because, you know, perhaps and from what we were talking, my understanding is that is not necessarily inadequate stock growth itself. It's more a stand problem, right? So maybe we have, like, the plants that are there are maybe growing appropriately or accordingly to what we wish they would, but maybe we just don't have enough plants there to give us the yield potential. So on an area basis, we have fewer plants. But that's a good point. I mean, and maybe it could be. And I actually, to tell the truth, I don't know the answer to that. Maybe this could be a good assumption as well.
Okay, thank you.
Okay, so yield goal is the main thing, right? Now I want to tell you, knowing of this field, all the layers that we have used, that we have generated, how can we use, or what layer can we use to define yield potential? How would you do that for this field? Spen, what do you think? Okay. Okay. So I like where we're going. Let me just redirect that a little bit. So Span was saying that we could use the spatial temporal areas to define the yield potential. That layer itself, it's not very useful for that, because that doesn't have, because we need a yield value, right? So if you look at this table here, we need to have a yield amount that we're expecting. And those layers have high or low, or maybe stable high, stable low, and stable. Those layers themselves don't have the actual values. But we do have the yield monitor data that we clean, process, interpolated, right? And those do have the actual yield values, the absolute values that we need to then connect with this table. But that's right. I mean, we do have yield data, right, for 3 years for this field. So why don't we maybe use that data to define our yield potential, right? So let's do that. So I left you some chunks there that you can just go ahead and run. First one, again, is just with all the packages that we'll need. The second one, please go ahead and run the first and second one. The second one is just defining that theme of the map, just to make it look cleaner. And we don't have to be typing this all the time. And then, so we have yield data for 3 years. So maybe let's just bring in all those 3 years and see how we can use that to define yield potential, not just on a field basis, but on a zone basis, right? So come down here to the next chunk where we have the 3 dots. Please go ahead and delete those 3 dots. So what we're doing here is bringing in the yield of 2017 that's been clean interpolated, that we created this layer, if you guys recall. However, I was speaking with Dr. Velides the other day, and we noticed something that we actually missed the first time around, which is, I'm just going to print this and ask for a summary just so you can see. So these yield values here are actually very high and perhaps higher than what they should be. And Dr. Velides mentioned that perhaps they are the cotton seed values, the mass values, and not the actual cotton lint yield values. For us to go from that mass value to the lint yield value, there is a conversion parameter that we use that is 40%. So 40% of the, let's say, unclean cotton seed, 40% of that is clean lint yield, which is what we normally want to work with. So let's just create, so right after that pipe, let's have a mutate. Let's create a column called yield 17 underscore LBAC for pound per acre. And this column is basically going to be this IP yield pound per acre variable that's already in this data set times 0.4. So again, the column that we already have in the data set is a bit too high. So we're assuming that is the unclean mass amount of cotton being harvested, and we're transforming that to clean lint yield, cleaning away in the sense of being like lint and trash together.
So yeah, perhaps a better term would be ginned rather than clean. I mean, it's the same thing, but just so those of you who are familiar with cotton, this is when you gin it, you remove the seed and remain wet.
Perfect. Thanks, George. So yeah, this would be the ginned value then for this data set. And then after that, I mean, we can just run it and print it. So you see, we have now this column here, yield pound per acre, yield 17 pound per acre, but we also have these other columns here that now we don't need anymore. So I really just want to do a select. So add a pipe there, that's called dplyr : select. And I really just want to select this column that we just created and the geometry. So it is, because it is a spatial object. So if we just run that and print it, you should really have 4,032 rows, only have those 2 columns that we selected. And if we come here, we want to make sure it is the proper CRS. Always the things we're looking for in here, right? And if we do a summary, we see now that these values have been reduced in 40%, and they're more within the range that we would expect for this field and for cotton overall. Okay, so we brought in this yield data from 2017. Let's do the same for 2019. I left you 3 dots there, which is basically just applying the select. So for 2019 and 2020, the values were already within the range. So they were already the gen version of the data. So let's just do a dplyr select. And you know what, I'm gonna comment off the pipe and run it just to first import it so we can see the names of this data, of the columns on the data set. So I'm gonna uncomment my pipe to now continue. We want to select this IP yield pound per acre, but I want to rename it. And the select function allows you to do both things at the same time. So I want to call this yield 19 underscore LBAC for pound per acre, and say that that is going to be equal to this current column here. And then also select the geometry. So the geometry we're not renaming. We're just renaming the yield. And then if you run that, we print it again, we see that we have the column, 4,032 rows. It is the proper CRS. Let's just check a summary very quickly. We see the values make sense. No negative yield values as we would not expect because this has already been cleaned and interpolated. Good to go. And lastly, let's do the same for the 2020 data set. I already left you the code there because we just did this step above for a different data set. So you could just go ahead and run it. We also want to inspect that it has the proper number of data rows. It has the proper CRS. And also that on the summary, that yield values make sense. And they make sense, all good. So this would be kind of that these chunks, we're kind of doing a little bit of exploratory data analysis. We don't have like a dedicated part of the script for that because we have already worked with these data sets in the past. We know that they should be in good shape, so we're not going to dive too much into that. Okay, so we have now the yield values, the absolute yield values for 3 years. But how do we connect those with the zones? Because none of these layers that we just brought have a zone column, right? That zone column is what we just created in the previous exercise, is that zone ST GeoJSON. So let's just import that. I already left you the code, don't have to do much on the code, just run it. And we're just going to quickly inspect it. So zone ST has fewer data rows. And this, I think this is, if I recall correctly, this is because of that elevation layer, like the terrain layers that have fewer observations around the boundary. But notice that, so I'm bringing in the zone itself, and I'm also selecting just the variables I need, because the zone object had a whole bunch of variables, of other columns there. And for this exercise, we really don't need all that. So I'm just selecting the ones we need, which is the zone and the geometry, because the goal here is to have a final data set that's going to have yield in 2017, another column for yield in 2020, or sorry, 2019, another for 2020, and then another fourth column with the zone ID. So this is the goal. If you come below here on the chunk, I already also left you everything here. I just want to walk you through to see what we're doing. You don't have to code anything. So we're starting with that zone ST, and we're doing a spatial join with first yield 17, and then yield 19 and yield 20. If you run all this and you print, this object called zone yield has exactly what we needed, which is a column called zone, and then, well, the geometry, which has to be there, and also a column for each one of the yield for each one of the years, right? With the absolute yield values, not high, low, but actual absolute values, okay? So if you come lower here, this is really, this chunk here, a lot is gonna go on, and we're gonna go step by step, but this is the key chunk of the variable rate fertilizer calculation of this exercise. So let's go very slowly here. So first thing that we want to do in this chunk is calculate the yield potential based on all 3 years of data. Originally, I had calculated that as the mean yield across all 3 years for each one of the zones. After that, I was thinking more about it. I decided to take a different approach. When we get to that, we'll talk about it here in a second. After we calculate yield potential, we're then going to use that table and the formula that drives this table to set. So we have our yield goal based on that yield mean. We're going to use that in this table, define the total nitrogen rate, define how much of that we're applying split or side dress. And that is a nitrogen rate in nitrogen units. So then we have to define what is the source of fertilizer we're using, transform that nitrogen rate to a source rate, and finally calculate how much of total of that source we're going to need for the whole field so we can order that amount and have it available for application. That's what we're going to do next. So let's go step by step. I want to call this object here VRN. So if you can come to this chunk, we're going to start doing some magic here. Add the assign symbol right there. We're going to begin with this object that we just created above, which is zone underscore yield, which I'm just going to print it again. It has that zone column and also the absolute yield values for all 3 years. And the first step here is for us to calculate the mean yield for all these 3 years. However, for that to happen, at least in the way that I want to show you, we have to have one column that has yield values for all 3 years in just one column. Right now, that information is scattered across 3 columns. To reshape our data from this wide format to a long format, we're going to use a function that we have used before that is called pivot underscore longer. So what this function does is we're just going to tell it what we do not want to pivot. So what we do not want to make longer. Our goal is to take each one of the yield columns and stack them below each other. So let's say what we do not want it to stack. So for that, we do a minus C. So remember, C is for concatenate. And then here we're going to say that we do not want it to stack zone, neither geometry. But everything else we want it to stack. So if we just run this and print it, you see now that we still have a zone column, we still have a geometry column, but everything else, which in this case were the 3 columns for yield, have now, the values came under a new column called value, and the name of the previous columns, which were the yield 17, 19, 20, are under the name column. And now the number of rows has triplicated pretty much because of that. Okay, so now we have a column with all the yield values. And I want to use all those yield values which span across 3 years to calculate a yield potential by zone. Because I want to do something by zone, by another variable, we need to do a group by. So let's add a pipe and do a group by zone. If we just run this, nothing happens. The data set is still the same. Behind the scenes, it created the 2 groups, but it hasn't done anything yet because we have not asked it to do anything yet with the groups that we created. So that's what we do next. I want to add a pipe here, hit return, and we're going to use a function called summarize, which again, we have used in the past. So what we want to do is I want to call this function yield potential, say equals. And here at first, let me show you what I did at first. I asked for the mean. Well, let me ask you here. What column we're going to ask the mean of? What value, what name we need to add here to get the mean? As far as our data is named right now, our columns are named.
Name.
Do you think name?
Oh, sorry, no, value.
Value, yes, because value is the column that has all the yield values, right? So that's exactly it. So if we do this, we run it and we print it, this is what we get. So we basically went from 11, or I don't even know how many rows we had. Let's just quickly do here. A lot of rows, right? So yeah, 11,000 rows. We went to 2 rows basically, which is the mean yield values across 3 years for each one of the zones. However, I was thinking about this and going back to my soil fertility classes and thinking about, I don't know if the mean, I mean, we could use the mean, but I don't really know if the mean is representing the potential of these areas. And it is common that we use a certain percentage of the maximum. And in some cases, we use the 90% of the maximum, or in other words, perhaps the 90th quantile of the total yield distribution. And that's what I decided to do here. And perhaps it's a good stopping point just to ask somebody else, if Dr. Velides has any thoughts, what should we use as the goal, or the yield goal across 3 years for 3 different zones? Is the mean good enough? Is that going to be underestimating the potential because the mean is below the potential? What do you think? Any thoughts?
Think of yourself as a farmer.
I think probably, I don't know, the averages of average per zone, maybe could be a good potential yield.
That's what we're doing here, right? Right at this point, we're getting the mean per zone over 3 years. And just to give you an idea, because this is, so you don't have to do what I'm going to do next, but just I want you to see these numbers, especially the max. I want you to see what was the maximum value of yield for each one of the zones. And maybe that's going to help us to define better. So while, for example, for the high yielding zone, the mean is 1400, but the maximum observed was 2700, was more or almost double the mean. So if you use the mean, are we underestimating the actual potential of the zone? Should we use the mean anyways? I guess it's a good conversation. I don't know. To tell you the truth, what I decided to do was to extract the 90th quantile of all yield over 3 years for each zone and define that as the potential. I know there are different ways of doing this. But I guess that's what I want to have us doing here. Would you agree that's a good approach, George? What do you think?
Yes, I think so, because what you don't want to do is create the situation where you are biasing yourself towards lower yields because you didn't add enough resource.
Right.
So this may mean that you've got that you're wasting a little bit of fertilizer in places because we know that those zones we created are pretty large. But it also probably means that you will likely ensure that you have high yields in the areas that have that potential within each zone that have higher potential than the average shows, like this 2700.
Right. Yeah. Perfect. All right. So instead of having the mean, let's just change that function to quantile. And we need to add another argument there, which is 0.9. So we're going to extract the 90th quantile of the yield distribution across 3 different years for each zone. So if we do that and we just print here, now, as we would expect, these values are greater than the mean was. So we're going to use this as our potential for each one of these zones. And as we were expecting, we do see a yield potential higher for the high yielding zone compared to the low yielding zone. At this point, since we coded high or low based on the key means on the previous exercise, at this point, we should always be getting the same result for high and low. If you have flipped, if your low zone is actually higher than the high zone, you probably did the wrong coding on that if else that we did previously. You need to go back to that and fix at some point. Okay, so now we know yield potential. Now let's look at this formula here, right? So what happens is the yieldable values of this table are actually, perhaps one of the zones is kind of similar, it's kind of close, but both of our yield potentials are greater than the values of this table. What happens if in that case? So if you think of it, this table here is actually coming from a simple linear regression. And if we just deduct or are able to realize what are the coefficients of this regression, we can just replicate this. Instead of having a table, we have a formula that we can apply to really any yield goal, not just the bins that we're seeing here on this table. We're not going to go too much into how to do that, the process itself. I just want to tell you what is the formula that I extracted from this information. So for that, let's just create a column here using the mutate function that I want to call total and rate underscore pound per acre. Oops, sorry, I changed. Here. So the total and rate is going to be a formula that again is coming from that table. The formula is 15. So 15, it would be the intercept of the linear regression plus our yield potential value, which is a numerical value right here. So plus yield potential times 0.006. Or I'm sorry, 0.06. So just 1 0 after the dot. So this is the formula that represents that table. If we run this, just to make sure that our values make sense, we see that we have a total in rate of 137 pounds of nitrogen per acre for the high yielding zone and 114 for the low yielding zone. Which it makes sense, right? I mean, it's greater than what we're seeing here because our yield potentials are greater than this table has. But that makes sense. Okay, so basically the 15 plus yield potential times 0.06 is the formula behind the table that we're seeing on the document. Okay, so if you recall, you can add a pipe there, but what we talked about earlier is that our yield potential should be adjusted upwards in 25% because we have cotton following cotton. That's the assumption that we're going in here. So to do that, we do another mutate. We're gonna call this total and rate underscore ADJ for adjusted underscore pound per acre. And this value here is basically going to be the previous one that we created. So the total and rate pound per acre times 1.25. So that makes sure that we're adjusting this 25% upwards. Does that make sense for everyone? Does that make sense? Okay, so if we run this and we print it, we see now that our original end rate had been increased by 25% because we're assuming that cotton is following cotton. Okay. So now what I want to do next is we know our total end rate, and I want to tell you what I want to do with this field. I want to have a pre-plant or at planting application of nitrogen, and then I want to have one side dress application. So let's first calculate what would be our pre-plant rate. So let's just add a pipe, hit return, use mutate to create another column. I want to call this, sorry, I'm gonna start getting very long with my column names, but I want them to be clear. So that's the reason. So I want to have PP for pre-plant underscore total and rate underscore ADJ for adjusted underscore pound per acre. Well, that's a long column name, but it has all the information we need right there to not get confused. So if we go back here, it says that apply 1/4 to 1/3 of the recommended and at planting. So let's do that. Let's use one of those values. I want to use 1/3. So of the total end rate, I'm going to use that. So you can just copy that from above. So the pre-plant application is going to be the total times 0.33, which would be 1/3. Okay. So if we run that and we print it, we see that now our pre-plant is going to be 57 pounds of N per acre for the high zone and 47 pounds for the low zone. Now, something very interesting is we are not interested in applying variable rate at pre-plants. We're only interested in applying variable rate at side dress or in season, right? With that, now that we're going to calculate the in-season application, we have to deduct one of these values. If we just deduct both of these values for each zone differently as far as the pre-plant, that is assuming that we're doing variable rate pre-plant as well. And again, I just said we don't want to do that. So instead of just doing the in-season being 0.66 of the total, I actually want to do something different. So let's do a mutate. I want to call this IS for in-season. Total and rate underscore ADJ for adjusted underscore pound per acre. And that's going to be pretty much our total N rate adjusted that we did. So the complete N rate minus one of these values here. So I decided to use minus 48. That was the pre-plant application rate for the low yielding zone. So I'm basically assuming that both zones are going to get 48 pounds of N per acre at pre-plant. And then deducting that pre-plant application from the total gives us our in-season side dress application. So if we just run that and print it, we see that our in-season rate is 124 pounds of N per acre for the high yield zone and 96 approximately for the low yield zone. Okay, so now we know how much we're applying nitrogen on a nitrogen basis for each one of the zones in season. So in season variable rate, pre-plant or at planting fixed rate. Okay, so now here's my question. I want to tell you that for our side dress application, so for our in-season application that we're varying space, we're going to be using urea ammonium nitrate solution fertilizer that has a concentration of nitrogen of 28%. However, it is a solution. It is liquid. How do we go from a mass unit that is pounds of nitrogen per acre to convert that into how much UAN liquid solution we're going to need using that nitrogen rate that is in mass? So going from mass to volume, pretty much. What piece of information we need here to do that conversion?
The volume ratio.
Sorry, can you say that again?
The volume ratio of the fertilizer that we will use, right?
Yeah, so what we need here is basically going to be so we have the concentration. Now we need to know the density of that solution, or sorry, we need to know how many pounds of nitrogen we have in a gallon of UAN 28, and for that we need to know the density. And so this information of density is going to be in pounds of UAN per gallon. And it is something that we can normally find as information in the label of the product or MSDS sheet of the product. I just want to show, I brought a couple of sources here. I just want to launch one of them just to show you where that would be. Let me see here. Where did I find that? Let me just do a search. Okay, so the density, and sorry, this is the MSDS for UAN 28% from Agrico, and they have in some place here in this document that the density of their product at least is under a certain temperature. It is 10.67 pounds, or what was the unit again here? Yeah, pounds per gallon for the 32%. Well, I'm sorry, it's 1067 for the 28% UAN solution, and it is 11.08 for the 32% nitrogen solution. So one very important point that I also want to make here is UAN across the US is sold in 3 different concentrations of nitrogen, 28, 30, and 32%. And each one of those concentrations have a different density, which is important when we're doing the conversion we're going to do right now. So it's important for us to really know what is the concentration of nitrogen in that solution for us to do this math properly. So in our case, we're assuming a 28% UAN solution. So we're going to use this value of 10.67. So if you just come back to our script. So I wanted to create some objects just so we track what we're doing here. And in this chunk, we're going to calculate how much pounds of nitrogen there is in a gallon of UAN 28%. So this value here, the density of UAN 28% density in pounds of the product of the source per gallons that we just got from that the website is 10.67 pounds per gallon. And we know that the concentration of nitrogen in this fertilizer source is 28%. So let's just say 0.28 in a fraction ferment. And then for us to really know how many pounds of nitrogen there is per gallon of this source, we basically just multiply. So this is going to be a multiplication of the density by the concentration. So you're going to have to run these objects for that to work. And then finally, we get to the result of this multiplication. That is going to be the pounds of nitrogen per gallon of product. So approximately 3. So approximately 3 pounds of nitrogen per gallon of UAN 28%. Now this value here that we just created is what we're going to use next up here. So let's add a pipe, hit return, and come back here as well. And what we're going to do now is a mutate that we're going to create a column called UAN rate underscore gal AC for gallons per acre. And this is going to be our in-season total adjusted and rate, which we just calculated above, divided by this number that we just found. So let's just call it 3. Let's just say that was 3. Okay, so if we just run that and we print it, these are how many gallons per acre of UAN 28% nitrogen we have to apply to each one of the different zones. Now, this is a fraction here, and it's not going to look nice when we plot it. So I just want to do another step here, which is adding a pipe, doing another mutate, and using the same column we use. So UAN rate gallons per acre, I'm going to say equals, I'm going to use the function round. And that function takes a variable. I'm going to use the same variable. So we do UAN rate gallons per acre, add a comma, and I want to add a 1 because I want to round it to 1 decimal place. So if you do that and you print it, we're just basically have now that UAN rate in gallons per acre rounded to 1 decimal place. Okay. So this is pretty much it. These are the numbers that we need to apply variably, either on a nitrogen, pounds of nitrogen per acre unit, or in a product, gallons per acre unit for this field for those 2 different zones. So let's plot this. Let's see how this looks, how this actually looks like. Oh, actually, before we do that, I want to do something else. I want to show you something else before we do the map. So, okay, we know the total rate of product, and we need now to know the area of each one of those zones. So we can apply, we know how much area we have, what's the rate of product. We multiply those 2 to know how much total UAN we should purchase for this field to make this application. So let's just go through that calculation here in this chunk. So we start off with our variable right VRN object we just created, add a pipe, and we're going to create a column. So we use the function mutate. We're going to create a column that is going to be called area underscore M2 because that's going to be in square meters. And because this is a spatial object, it works very nicely to use a function called st underscore area. And we just add a dot in between the quotation marks. So it has a placeholder for the data set coming in. So if we just do that and run it, we see that now there is a column in the end that is the area in square meters for each one of the zones, which is pretty cool. However, our rate is in pounds of UAN per acre. So let's, excuse me, transform this area here to an acre basis. So we do a mutate, We're going to call this area underscore AC. And that's pretty much going to be area m squared divided by 4047. If we run this and we look at that, even though the number here represents acre, but it's given us a unit of square meter just because the type of object created by ST area. So to force this to not be called m squared anymore, let's just come back here and use a function called s.numeric, open parentheses, and then close at the end. So basically have that area divided by 4047 inside the function s.numeric. So we force it to be just a number and not be seen more as a unit column that has that meter square unit. Okay, so we see now we have 47 acres in one of the zones and 44 on the other. So they're pretty similar in area. And now what I also want to do here before we multiply rate by area is if we order exactly how much we're going to apply, maybe something happens, maybe we're going to run short. So I just want to increase well, we're actually increasing afterwards. So sorry, let's just add a pipe, add a mutate here. And first you want to call this UAN underscore gal for gallons. This is going to be the total gallons needed for this field. And that's basically going to be, let's just open and close parentheses just to have like the value that the math that we're going to do within those two parentheses. That's going to be our area in acres times our UAN rate in gallons per acre. Okay, so if we just run that, look at it. This is our total UAN in gallons for each one of the zones. But I want to come back here and I just want to multiply. So get outside of this parentheses and add an asterisk and multiply this by 1.2, just so we calculate a total that is 20% more than what we need for this field. So we have a little bit extra fertilizer available in case we need for some reason. So multiply by 1.2. And now we do have this data here. So the total UAN for each one of the zones, which when we are ordering fertilizer, it doesn't really matter how much we need per zone. We just need to give one number of what we need. So lastly, let's add a pipe and let's do a summarize where this is going to be, let's call this total UAN underscore gal. This is basically going to be a sum of how much we need for each one of the zones. So let's use the function sum. So sum of UAN underscore gal. So this returns us one data row saying that we need about 4,000 gallons of UAN 28% for this field to be delivered so we can apply the proper amount that we need. Okay, so we're going, let me just see here. I think we just have, yeah, we have a few more chunks. I think I'm going to continue here. It's probably going to take another 10 minutes. If anyone has to leave, please do so. I want to finish this. And before anyone leaves, I just want to tell why. So I will be traveling and not be able to teach next Monday or Wednesday, but I do want to give you the final project assignment before then. For me to do that, I have to finish the class, definitely finish this class today. And the profitability one is going to be beyond it. So I will probably record myself teaching the profitability exercise. If you're interested in learning, you can go through it. I'm not going to require you to go through it or even to have that as part of the project. You're not going to have to do that in the project. I will have that just in case you're interested.
Leo,
yeah.
So based on what we discussed earlier, would you be willing to continue this on Friday and we can just, since we are canceling classes unexpectedly Monday and Wednesday because of your sudden trip to Brazil, students can have those days off to watch Dr. Lacerda's presentation as a recording. And maybe we can continue this on Friday, and so if people have questions, maybe they can ask. We can maybe finish it a little bit more casually. Would that work for you, or do you have plans for Friday?
No, that definitely works for me. We can do that. Yeah.
Okay, so I think that's what we should probably do, just to make sure that, you know, though everybody has a chance to digest this, ask questions. And so instead of canceling class on Friday as originally scheduled, you're having Monday and Wednesday next week off, essentially. So you'll have to watch Lorena's recording, seminar as a recording, and then we'll just meet for class on Friday to continue this at a sort of a, so Dr. Bassos doesn't have to rush through it and you can follow it a little easier.
That sounds great. And so let's do this. Let's stop right here. We're not going to create the maps yet or do anything of what we're going to do here. And so Friday, we're going to finish this. It's going to be very quick, probably 10 minutes. We can finish this exercise. We're not going to have the profitability exercise, as I was telling you. I will record that myself. If you want to watch it later, you can. You don't have to. But I will finish writing the project as I'm envisioning this today, between today and tomorrow. So Friday, I can actually tell you exactly what we're going to do, what is the data, what I expect from you, and what I need to turn in the deadline. So we can really have a more, I guess, slow-paced conversation about the project, which is basically going to require you to do everything you did up until now, but for a different field, different data set, and kind of think through all the steps we did, but now on your own, and really judge what is needed, what is not, how is this data different, do I have to do it differently? That's all something I want you to go through and think about it. So that's what the final project is going to be directed to.
So there's going to be a final project and a final exam?
No, the final project is the final exam.
Oh, and also, I just remembered very quickly here, because we did finish the zone assignment or the zone exercise, I had an assignment for you for that exercise that I think is going to be very critical to understand. I have posted that on GitHub already, but I will send you an email with more details about that. But it's going to be due next week. That is, comes actually before the final project itself. So another assignment, I'll send you more details by email. All right, I think that was all for today then. I'll see you all on Friday and we'll finish this and talk about the project. Any questions?